So the fifth question. This question is it has a personal story about it. I would tell that later, but right now let me finish the explanation. So Kirchhoff's second law we have seen yesterday as well. Sum of the potential difference is equal to sum of the EMF in a closed circuit per unit charge. And the second part asks what is the conservation law, or to conservation of which quantity it is related. Kirchhoff's second law relates to the conservation of energy. Kirchhoff's first law relates to the conservation of charge. The B part, it is a question on potentiometer about balancing and finding the EMF of a cell that is unknown. So we have seen the theory of this question. If you are not sure, so potentiometers has quite a large theory. So this is the scenario. Okay. So go and check notes, page 2. So the question says that the wire is 1 meter and it has 4 ohm resistance. Okay, so so according to the question, the length of the potentiometer wire is 1 meter and the resistance is 1 meter and the resistance is 4 ohms. The EMF of the cell is 2 volts, and bad news, it has internal resistance 0.5 ohms. The current through the cell is I. Cell B has EMF E and internal resistance R. The current through the cell B is made 0. So when we are talking about the situation that we are talking about is when the balancing has been achieved and there is no current through the lower circuit. Applying Kirchhoff's second law to the circuit CXYDC to determine the current I. So they are asking you to apply the Kirchhoff's law and they are giving you the loop that you should be concerned about. So if you look at that loop CXYDC, Kirchhoff's second law is simple. The sum of EMFs in a closed circuit will be equal to the sum of potential differences. So you just take a very peaceful walk from C and you try to locate each EMF that you come on the way. So first we have the 2 walls, then I'm walking and CX. From X I'm going to take the wire. I'm not going down, so I'm going in this route. No EMF in this route. Yeah, so the only EMF in that route is the 2 volts. So applying Kirchhoff's law, the EMF 2 volts is equal to the sum of potential differences. So now I'm going to take another lap and see what are the potential differences there. So the section of the wire CX is of negligible internal resistance. Then we have the wire XY which has resistance, right? And the resistance of the wire XY, X to Y, is 4 ohms as stated in the question. Then we have a variable resistor and it is said in the question that the value of the variable resistor when we achieve the balancing is 2.5 ohms. So it's said here the variable resistor R has a resistance 2.5 ohms. So you have a 4 ohm, a 2.5, and you have this internal resistance, but basically an internal resistance for all practical uses. We are treating it like a resistor that's attached to the circuit. So that 0.5. So basically the potential drops through the circuit in that loop CXYDC is the potential drop in the wire, potential drop in the 2.5 ohm resistor, and the potential drop in the 0.5 ohm internal resistor. And from Ohm's law, V is equal to IR, the potential drops will be the current times the resistance value. And the good news is the current is the same through all these three components, the wire, variable resistor, and internal resistance, because we are talking about the balanced situation, and in the balanced situation there is no current through this lower circuit, which means that the entire I that is coming is going through the wire, the potentiometer wire. So if you have understood that, then the application is simple. You just have to, the I is the same, then the resistance values added together, the 4 ohms from the potentiometer wire, the 2.5 ohms from the variable resistor, and the 0.5 ohms from the internal resistor, and this should give you a current value of 0.286 amps. Then the next part of the question asks you to calculate the potential difference across the length of wire xj. So now the xj, the j is the balancing point in the wire. So you need to find the xj. Now the issue in this part is, whenever we are talking about potentiometer, we are very much used to the idea of dividing the EMF in the ratio of the resistors that are there. So that's the fundamental principle of a potentiometer. It divides one EMF, right? So if you have a 2-volt battery, you can't take a bread knife and cut it into 1 volt and 1 volt. Rather, you need a potentiometer and a couple of resistors which are equal to get it 1 volt, 1 volt. So that's the fundamental idea of a potentiometer, as we have seen in the theory. But so it's very tempting to use that idea, that ratio idea, trying to, so you can say there are the ratio ideas here, sorry, in this case this would be, the ratio idea would be this ratio. The the terminal potential difference V will be divided according to the ratio of R1 and R2. But that's what I am saying again. For that, you need to know the potential that is dropping across the potentiometer wire from there to this end. So if you look in this question, you know that the EMF is 2 volts, but you have no idea that how much of that is falling across the region XY. First, some of it falls across the 0.5. Then some of that should fall across the variable resistor. Only the remaining is available for the poor wire. But yes, if you have known what is available for the poor wire, let's say that the remaining is 1 volt from the 2 volts, then you can simply divide it in the ratio of the length. This is 0.9, this is 1, so 0.9 volts would fall across xj and 0.1 volt will fall across jy. But unfortunately we don't know that. So it's possible that some really enthusiastic persons would like to calculate the potential drops across the variable resistor, the internal resistor, and subtract it from the EMF to find the potential drop across the wire, and then divide it according to the ratio. And to do that, he would think, yes, I can do that because I know the current value by now, which is 0.286 amps, and I know the variable resistor value, I know the 0.5 ohms. So I will calculate that. I will multiply the current by the variable resistor with internal resistance and find the volts that are dropping there, then subtract it from the EMF and find the volt that is dropping here, and find divide it by the ratio. While you can simply find the resistance of this 0.9 meter, which is simple, and then multiply that resistance by the current value, and you got the answer. So the only issue is you could be misdirected in the very beginning because of your obsession with the ratios when it comes to potentiometer. So that's why they are kind of guiding you through the Kirchhoff's law. So you would kind of be brainwashed back to V is equal to IR era. Okay, so you have 1 meter wire which is 4 ohms, so 0.9 meter, it is simple math. R is equal to rho L over A. Yeah, the wire is uniform and cross-sectional area is uniform, hence the resistance 4 ohm will be divided. So 1 meter has 4 ohms, so 0.9 meter would have 3.6 ohms. So this is the resistance of the part XJ, the one which we want to calculate. So you know the resistance value, you know the current. So the drop across that is 1.03 volts. Simple. Then they're asking you to calculate, if you go through the part, state the value of the EMF of the second battery, the bottom one. Well, at the balance condition we have learned it's the EMF of the battery would be equal to the potential drop across the part that is balancing it. So in case you have forgotten it, so here it is, page 2 bottom. When balanced, the EMF of the cell is equal to the potential drop across the part of the wire. Okay, so 1.03 volts is the potential across the part of the wire, that would be equal to the EMF. So the answer is 1.03 volts. Then the question asks you why you don't have to know anything about the internal resistance. Because there is no current through the lower circuit, right? So you can have as much internal resistance as you need, but only if you have current, then only you will have the potential drop. Yeah, right? So the resistance itself doesn't mean that you're going to have a potential drop. So a current should pass through it for that to happen. So when you take the lower circuit, there's no current passing through it, so I is 0, so R can be as huge as it wants, no point, it will be still 0. It's like a person is very strong and built, but he has a very kind heart, so he's not going to hurt anybody. And if a person is really violent deep inside, then even if he's weak, he's going to be very, very dangerous. So I don't know why I said that. Okay, so let me tell you the story.